Now let's look at another statistical test called the chi-square test. It is used for testing some goodness of fit. Okay, so by that I mean something like this. Suppose we have some kind of random variable that varies from 0 to 5. Okay, and if we make a series of experiments, like 2000 experiments, observations, then we observed 59 times uh, the value of 0 and 316 times the value of 1 and so on. So we have these observations of the random variables. Okay. On the other hand, somehow we have theoretical estimates, theoretical prediction of these observations. So if we have some probabilistic model of this phenomenon, so we can calculate the expected number of observations in each class. Okay, so there are 6 classes here. So these numbers here are theoretical estimate. Okay. Then we want to ask, how does real observation fit with the theoretical expectation? Okay. So are they similar enough, or are they significantly different? So if they are significantly different, then the theoretical prediction is wrong. Okay. So we need some better model for these observations. Okay. So to do this, we can apply the chi-square test, but what kind of statistic do we need? And here's how you calculate this. Suppose, let's say, we have k classes. Okay. So in this case, in this example, we have 6 classes. So k is 6, and we have observations for each class. So observed value, let's say n, I, so I from 1 to k. These are observations. Okay, this means class, okay, n1, n2, and so on up to nk. So this means class 1 was observed n1 times, and class 2 was observed n2 times, and so on. And for each class, we have some theoretical expected number. Okay, theoretically expected numbers. So this is I from 1 to k. So it's expected. Let's say frequency. So these are observed frequencies. So using this and this, we define the chi-square statistic by this. From 1 to n, no, to k, actually, because there are k classes. So this is ni minus ei squared divided by ei. Okay, so this means ei cannot be 0, right? Okay. So, and we can show that this chi-square thus defined chi-square statistics follows approximately the chi-square distribution. Chi-square distribution with how many degrees of freedom? We have k classes, And actually, this is a little bit involved. It follows the chi-square distribution with k minus 1 minus some number p, degrees of freedom. So what is this p? So this p is, how can I explain this? So this p is the number of parameters uh, which have been independently estimated. Independently estimated from the data. Maybe it doesn't make sense at this point, but we will explain this with real examples later. Okay. So anyway, this uh, quantity follows approximately a kind of chi-square distribution, but the number degrees of freedom may be a little bit strange. Okay, it cannot be just guessed from the number of classes here, but we need to find some adjustable parameters, that can be independently estimated from the data. Okay, so in this particular example, what is the value of p? Okay, in this case, we actually don't need to estimate any parameters. So the data is just this, that's it. And the expected frequencies are just this, and that's it. So in this particular case, this this chi-square statistic follows the chi-square distribution with, so there are 6 classes, so 6 minus 1 is 5, so 5 degrees of freedom. Okay, so if you calculate this quantity chi-square statistics for this particular data, okay, we have these differences here, so we square it and divide by the expected frequencies, okay, and add them. So if you do that, I think you should get from this data, I think you should get chi-square statistics of 4.78. Yeah, you should check. So is this significantly large? So to check that, you look at the table of chi-square distribution. Where is it? This one. Okay, so in our case, we have 5 degrees of freedom. So we look at this column. And if we are interested in 5% significance level, we look at this column. So we look at this number. So if the chi-statistic is greater than this number, then this probability here in this shaded region is less than 5%. So we can reject that the two distributions, this distribution and this distribution, they are different. However, in our case, it's just 4.78, which is far smaller than this value. So the difference of observed frequencies and expected frequencies are not significant in this case. Okay, that's the basic usage of the chi-square test. And we'll see more examples later. Okay, I think I should explain this example again. So this is actually a data of coin flipping again. Okay, so flip a coin 5 times in a row, and then count the number of heads in these five flips. Okay, and we do this 2,000 times. Then that means so in this particular case we observed 59 uh, no heads for 59 times out of 2,000 experiments, and one head in 316 times in out of 2,000 experiments, and so on. But yeah, that's fine. That's just experiments. And but how do we calculate this expected frequency? These are theoretical values. Any ideas? So actually here we are assuming that the coin is fair. So this number, let's say this is k, number of heads. Let's say these are random variables, the values of random variable h. So the probability of h being 0 is a binomial distribution, right? So 5 choose 0, p to the power of, actually p is, well, anyway, and 1 minus p to the power of 5, where p is assumed to be fair. Okay, so it's 1/2 exactly. And similarly for h equal to 1, so we replace 0 with 1 and so on. Okay, so this is how we can calculate the theoretical value. So uh, in this way we can compare our theoretical value and experiments. You know, this is another way to check whether a coin is fair or not. We assume the coin is fair and calculate some theoretical predictions and do some experiments and compare them to check it matches the theoretical expectation. And if it doesn't deviate too much, then we cannot reject our hypothesis that the coin is fair. Okay. So in this coin toss problem, things were easy. We have nice theoretical prediction according to our hypothesis. But in real situation, we don't have that kind of theory to estimate anything. Okay, so let's look at another example here. This is a table that shows the number of births in England and Wales in 1956. Yeah, I took this from an old book. And by sex and whether live or stillborn. Okay. So uh, each infant, like newly born babies, were categorized into according to their sex, male or female, or live born or stillborn. Okay, live born means they were born alive, and stillborn means they are born dead, unfortunately. Okay, so these are the numbers here. Okay, and the total is this. And the total of live borns are this, and stillborns are this. Okay. Now, here we are interested in whether live born and stillborn are independent of the sex. Okay. So how can we check this? For example, first, so assume they are independent. Then what does it mean? So independent means probability of male and live born. Okay, for example, should be expressed as the product of male and live born. Okay. We should uh, check this probability, okay? Probability from this category. So in this here, one of this and one of this, okay? Of course, we could do male and stillborn. Okay, if this holds, we don't know if it holds. Okay, okay. So in any case, this and this or this, and this and this or this. Okay, but don't do this. By the way, I've seen this in students' answer in some tests. So this is nonsense. Male and female. Okay, don't do this. This probability is always zero, of course, because they are mutually disjoint, right? So there's no way you can prove this holds. Okay, female. Okay, this is wrong. Okay, it's nonsense. This is always false. It doesn't hold. This is not zero. The right hand is not zero, always non-zero, but the left hand side is always zero, of course. This doesn't make sense. Of course it's not independent, because if you are male you are not female, and vice versa, so they are not independent. So that's not what we want to check here. We want to check whether live born or stillborn depends on the sex, male or female. Okay. Okay, so how can we check this? So if they are independent, then this probability, male and live born, should be expressed as the product of probability of male times probability of live born, right? So let's estimate the probability of live born, which is this number divided by the total number, right? 700,335, 716,740. So which is about 0.977 and so on. And you calculate the probability of male. So that is male, this number, 368,490, 716,740, which is about 0.514. Actually this is statistically significantly larger than 0.5, right? Males are always more than females when they are born, and looks like this is very universal. This is observed across the world. I think in Brunei also there are more males than females when they are baby. Okay, so if they are you know life or still is independent of sex, then we can estimate the number of live born male babies. Okay, so if they're independent, then we should have 16,740 times these probabilities. Okay, live times male. Okay, so if you plug in these numbers, this should be 316,056. Okay, so this number is written here. Okay, this is the number obtained by assuming these are independent. Okay, so we can also estimate the numbers of male stillborn babies. Similarly, instead of live, you calculate the probability of still, and you should get 8,434 and so on. And similar for female babies, whether live or still born. So we want to compare uh, these numbers with these theoretical numbers. Okay, assuming theoretical means we're assuming independence. Okay, so that can be done by calculating the chi-square statistic. So so this, okay, let's see. So this number minus this number squared divided by this number, theoretical number, and this number, observation minus prediction, squared divided by the prediction, and so on, and add them all. Okay, so if you calculate these numbers, I think the chi-square will be about 7.56 in this case. Okay, so this follows chi-square distribution, but with how many degrees of freedom? Okay, in this table we have 4 numbers. Okay, so k is 4. So okay, we always put k minus 1 and minus something p, right? So p was the number of number of parameters independently estimated from the data. So what are they here? In the previous case there were none, but in this case, we used these data observations to derive these theoretical values. Okay, so because of that we have to reduce the degrees of freedom. So how many data we used? Okay, we needed this number and this number, right? By the way, in order to calculate the values for females, we need this number and this number, but they are not independent, right? Because we know the total value. So once we know the number of, for example, number of males, we can automatically infer the number of females. So this doesn't count. And similarly, once we know the number of live-born babies, we can automatically deduce the number, derive the number of stillborn babies. So the number of independently estimated parameters is 2 in this case. Okay, so p is 2. So 4 minus 1 minus 2 is 1. Okay, so after all, this chi-square statistic follows the chi-square distribution, approximately follows the chi-square distribution with 1 degree of freedom. Okay, so let's look at the table. Let's see. Now we are interested in 1 degree of freedom, and let's look at 5% significance level. So the value is 3.841, and which which is smaller than 3.841. So looks like the difference, chi-square statistic is significantly greater than some significance level. So that means the difference between the observation and the theoretical value, assuming independence, so they do differ significantly. So that means our assumption that whether live born or stillborn is independent of the sex was false. So we reject the hypothesis. Therefore, they are not independent. So these are not independent of these. Okay? So this is how you can test whether something is independent of something else. Okay, let us summarize the logic of significance tests. Okay, first of all, we must have data. Okay, and then we have to have a null hypothesis which we want to test, or rather, which we want to reject actually. If we can reject it, then that's for sure. If we cannot reject it, we cannot say anything. Okay, so null hypothesis. So, these are usually meant to be rejected. And 3, the model, okay, by which we calculate some theoretical prediction. Okay, so this gives the probability. This model calculates the probability so of data given hypothesis. Okay, so yeah, we need some kind of method to calculate this probability, and that is called the model here. And we have to also give the significance level. Okay, usually we use 5%, or if you want to be more strict, we use 1%. Anyways, by the way, this is called p-value, right? But why 5% or 1%? Why not 1.5%? I mean, these exact values don't mean anything. If it's small enough, then that's okay. But it's just a convention that we use 5 or 1%. Okay. So that's the logic, basic logic of traditional null hypothesis or significance test. Okay. But remember, what we want to do is to test our hypothesis, right? Not test, but what we are doing here is actually testing the data based on the hypothesis. So that's not exactly what we want. What we really want is to test the hypothesis. So the probability that the hypothesis is true, that's what we want to find, given the data. So, but this probability is not calculated from traditional methods. But there are some methods that do use this kind of technique, approach, which we will study later. But anyway, see the problem here. If this probability of data given the hypothesis is small enough, then we reject the hypothesis, because according to the hypothesis, the probability of finding the observation it's so small that it's not probable, right? Therefore, we reject the hypothesis. So what if this probability is not small enough, like greater than 5%? Then we cannot reject the hypothesis, and that's it. It doesn't mean we prove the hypothesis is true. That's not right. We cannot prove anything here. We can just reject. It's a very negative idea, right? We can only reject. We cannot accept. Why? Because even if this probability is large, according to one of our hypotheses, let's pick another hypothesis which gives bigger probability. Okay. If the second probability is larger than the first probability, then what do you see? I mean, you know, we accepted this hypothesis. Suppose. So this hypothesis should be true. But what if we find another hypothesis that gives you a larger probability of the data we have? Then this should be more true, right? So our previous hypothesis should not be true. I mean, less true. So it doesn't make sense really. So anyway, we can only reject, not accept. Cannot reject doesn't mean accepting. It just means we cannot reject at this point. That's all. But actually, this logic sounds quite like science in general, right? Right? Scientific theories cannot be proved to be true. It can be only rejected if there are some, contradictory data, right? So even if there are no contradictory data up to this date, up to today, maybe tomorrow there will be another new experiments that will show some contradiction with the theory. So we can never be sure about our scientific theories. Yeah, so this logic of significance test is very similar to that logic of science. Okay, that's all for this chapter. See you next time.